Okay, so this is the last talk of this evening session. And our next speaker is Professor Allan Edmonds from Indiana University. And he'll be talking on playing with finite group actions on one complexes and homology. Yeah, please.
Thank you very much for the opportunity to join in this nice celebration. I made a slight change to my title. The one that was in the abstracts didn't have the first two words on there, so I hope you enjoy the thought. I know this is the last talk of the day for you. I'm going to be talking about finite group actions on one complexes and homology, and I say playing around with it for fun, kind of. What we're talking about is not something I was really planning on talking about originally. It was sort of I would call it my COVID project, a question or two that I had in mind, and the sort of thing I can ponder, I can think about while I'm going to sleep, try to answer a question or two that have been in the back of my mind for a while. So here are the sorts of questions I'm thinking about. If you have a finite group acting on a one complex, or any space for that matter, what are the representations on homology that can be realized as ZG modules? How many different ways can you realize a particular representation? And maybe a slightly more specialized question, how well does the representation determine the fixed point set? Part of playing around was to take this question, which could be relevant in any dimension, many other categories, surfaces, four manifolds. Those are places where I've looked at questions like this before. Reduce it down to its bare bones and see what's left there. So I had a particular question in mind. Just if you looked at a cyclic group of prime order P, how many different ways can it act on a particular finite one complex up to homotopy? So we'll get to that by the end. I'm going to try to have some pictures to carry. So I have a couple of slides of pictures here that can illustrate what's going to be going on, and maybe you can just keep the picture in your mind. You don't have to worry about all the symbols. The cube, the one skeleton of the cube, has a fourfold symmetry rotating around that vertical green axis that goes through the top and bottom face. If you think about what is that, try to distill out from that what the rotation actually looks like. Well, you can think of that top square as a circle that's being rotated in itself, and then you can think about the four side squares as circles that are being cyclically permuted. And then of course the bottom circle is just a consequence of the others. So there to the right, I've abstracted the situation. We have the red circle that's invariant and the blue circles which are cyclically permuted. You can even go up a little further and just pass to the quotient space. Of course, that's a covering map. I made the red circle a little smaller to kind of indicate that. So you see a covering of it. It's a cyclic covering over the red circle and a trivial cover over the blue circle. And once you have this nice picture, you immediately just read off what the representation on homology would be. There's a Z, that's a trivial class, that's represented by the red circle. And then there's a Z of Z4, four circles cyclically permuted. The cube has lots of symmetries, of course. Let's think about a threefold symmetry. I've drawn in an axis that goes diagonally through the cube there. Think of rotating by 2 pi over 3 around that blue dotted line. Of course, you see two fixed points in this case, so those are those big black dots. And you see a lot of extra stuff here again. So if you imagine shrinking down the edges to get rid of those extra vertices, you end up with a picture like the one immediately to the right, where you have two fixed points, and then you have three lines connecting the fixed points that are rotated among themselves. And then you have, having shrunk it down this way, you see three circles at one fixed point that are cyclically permuted among themselves. Again, you could pass to the orbit space and you have a fairly effective, more compact description of what's happening. You have two fixed points, you have a single edge running between the two fixed points, and then you have a loop at one end. You have to label those things because you know what's happening over them. So the ones indicate fixed points, and the C3 indicates the interior of the edge is covered three times cyclically. You can work out from this picture what the representation is on homology. The little loop at the end gives a group ring again, Z of Z3. The edge in the middle on the chain level, that gives a group ring Z of C3. But at the level of homology, if you try to write down the homology classes there, it takes two of those edges to make a homology class. And the sum of those three homology classes you get that way is zero. In other words, you're seeing a copy of the augmentation ideal. So those are the kinds of ingredients that will come up in what we're talking about. We're talking about homology, so I just thought to record a few obvious or standard facts about group actions and homology. Other characteristics multiply in a covering space. The orbit space homology is the invariant homology upstairs if you're using rational coefficients. You can get a handle on the fixed point set a little bit by the Leschetz fixed point theorem. For each individual element of the group, with a characteristic of the fixed point sets, the Leschetz number. Again, all these things are relevant in all dimensions, but this is sort of the lowest possible dimension where all of this sort of has a little bit of content to it. And finally, I might mention Smith theory, which is maybe the most familiar general machine of homology and group actions. Trivial homology implies, for the space, implies trivial homology for the fixed point set. Of course, it's well known in higher dimensions, you can't get such a situation, such a nice implication in general, but only if you restrict to P groups and ZP coefficients. In dimension one, those P's are not very relevant. You know, if you know the ZP homology, you know the Z homology and vice versa. So let's start the story with finite groups acting on trees, a subject which, of course, goes back to antiquity, I suppose, but kind of burst on the scene, you know, from a certain point of view in Sayre's seminar on trees. And this is sort of the starting point or the trivial case. If you have a finite group acting on a tree, then the fixed point set's non-empty. The fixed point set's a tree. And I would add the statement that the action itself is G homotopy equivalent to a trivial action on a point. I have a nice little picture of a tree there. I tried to color the pieces that could be permuted by a group action versus the part that's necessarily fixed. So you can imagine a Z mod 6 action on that tree with a Z mod 2 and a Z mod 3 that don't really interact with each other. From a not necessarily historical point of view, this is a nice starting point for a lot of investigations. There's a whole question of group actions on contractible spaces and what does that necessarily have a fixed point set. There's a very rich theory there in higher dimensions, one strand of which was dealt with by Bob Oliver, where he figured out what groups could act on higher dimensional disks without a global fixed point. Interestingly, there have been in fairly recent years some return to lower dimensions. There's some interesting questions about two complexes actually here. If you imagine contractible or acyclic two complexes, the final story maybe for contractible two complexes isn't necessarily known. I'm going to go off in a different direction, however. I'm going to stick with dimension one, but allow for more general spaces. in dimension 1, as opposed to raising the dimension. So here's an example of a small theorem. What if the representation on homology is trivial? And the statement is, if a finite group acts homologically trivial on a connected finite one complex, there are two possibilities. The generic case, the conclusion is that the global fixed point set is non-empty, and in fact, the action itself is G homotopy equivalent to a trivial action, and the whole space equivariantly deforms down to the fixed point set. When the Euler characteristic is non-zero, that's what happens. In the case, the other possibility is that there is no global fixed point. This is what happens as a possibility when the Euler characteristic is 0. And in that case, you essentially have a group acting on a circle by rotations up to homotopy. Another virtue of this little argument is that if you have a group acting on a space and it has some elements acting trivially on homology, you can adjust the action up to G homotopy so that that subgroup that acts trivially on homology actually acts trivially everywhere. So for the most part, in other words, we assume our representations are faithful representations now. So thinking about finite group actions on one complexes, I wanted to try to build a diagram that kind of puts the thing in a context of the different ways you can think about it. There's a connection between groups acting on a space, this purple or blue diagram in the middle. If you have a group acting on a space, a one complex, then you automatically have a representation in the outer automorphisms of the fundamental group. And if you have a representation in the outer automorphisms of the fundamental group, you automatically get an extension of the free group by the group that's acting. That comes about in this case because the free group in general has trivial centers, so that you have that short exact sequence I wrote up in the opening paragraph there, where you can now just pull that sequence back to the finite group. Some of my interest in this problem goes back to the 80s, where Zimmerman and Kohler showed that all these different perspectives are all equivalent to one another. In particular, if you have an extension, if you have a representation in out Fn, and then an extension of that sort, you can build a finite group action on a one complex that corresponds to that extension and induces the same algebraic information, so that you can then address algebraic questions by equivalent topological questions. The rest of this diagram has to do mainly on the left-hand side with the question of fixed points. So the issue there is you get a representation on the actual fundamental group. That is, you would be mapping into the automorphisms of the fundamental group. Well, that requires a fixed base point. And question at the level of the extension is whether that extension is a split extension. If it is, the group action has a fixed point, has a global fixed point. So I'm going to ignore fixed points for the most part for the rest of today, but in some points you have to carry the fixed point along, of course. Just a comment about equivalence here. When I'm trying to classify things, I'm taking this somewhat flabby description of G homotopy equivalence. Helps to simplify things and focus in on what's essential. The other thing I want to just mention is that I'm talking about groups up to conjugacy. So that might sometimes go by the term weak equivalence. I'm not distinguishing when I have a group G acting. I'm ordinarily not distinguishing a particular generator, for example, for a cyclic group. Otherwise, standard notions of equivalence. So let's forget the group action for a second What's the homotopy classification of one complexes? Finite connected one complexes. Up to homotopy, such a thing as just a wedge of circles. The standard one-liner is collapse a maximal tree to a point. More algorithmically, I might say successively collapse edges that have distinct endpoints down to a single point. You keep collapsing edges until you can't collapse any more edges that have distinct endpoints, and you arrive at your wedge of circles. The question is, what's the proper equivariant version of this process? Well, for that, we had to figure out what's the analog, what's the G analog of an edge with distinct endpoints. For this, you have to think about how can you collapse an edge without changing the G homotopy type, do it in the equivariant category. Well, whatever you do to one edge, you have to do something similar to each translate of that edge. So the upshot of this, eventually you see that what you need is that the orbit, if you want to try to collapse an edge, the orbit of the edge should consist of acyclic pieces. It doesn't have to be connected, but in graph theory, they call these forests. Each component is a tree, and then you could collapse that tree down to a point. So in the end, that's the right way to talk about this. And I call this G reduction. So if you have a G1 complex and you want to kind of make it as simple as possible within this G homotopy type, you can take any such edge, which I would call G collapsible, and we form the quotient space by identifying to a point each component of the orbit of the edge. And the result of doing this until you can't do it anymore is a reduced G complex. And here's one nice thing that you get out of this. You get it, at least you've improved the way the fixed point set looks. Instead of being some sort of random one complex sitting inside your bigger complex, your fixed point set at the very least has turned into a disjoint union of isolated vertices and wedges of circles. And by the way, all the vertices in that bigger complex are now among the fixed points. Because you can, as one of the steps in the reduction process, you can take an edge with distinct endpoints in the fixed point set and collapse it, just like we did in the non-equivariant case. So we want to build on this. Again, just a few words about something I drew pictures about at the beginning. When you have a one complex with a group action on it, it's some complicated graph with edges being mapped all over the place, and one can pass to the orbit space and label the edges in the orbit space and the vertices according to their orbit types or their isotropic groups. The two are equivalent. In the case of semi-free actions, which is what I'm going to be mainly focused on for the rest of the talk, is this gives a faithful representation of the action, and it allows you to draw a picture with many fewer edges to keep track of. Just as an aside, this business of labeling the orbit complex is not so effective when you have more complicated groups. There might be multiple ways you can construct a group action that has the same labeled orbit space, or you might imagine a labeled orbit space that doesn't correspond to any group action at all. So with all of that said, here I have a wordy slide that brings together, and I'll be drawing some pictures about each of these steps, a process of normalizing a group action onto one complex until you can get down to the point of answering all those sort of basic questions that I stated at the beginning of the talk. So if a group acts semi-freely on a finite one complex connected with a non-empty fixed point set, then the action is G homotopy equivalent to one in normal form. The first step is what we just talked about, reduction. So we can assume the complex has been reduced in that sense of not having any obviously contractible edges that you can get rid of, in which case the fixed point set is now a disjoint union of a bouquet of circles or single points. The next step is to think about how those different components of the fixed point set are connected. So you have several components of fixed point sets, and they had to be connected in some way. You can find some principal edges that connect them, since we've already taken care of all the fixed point set. And you can play around with the way these edges are attached up to G homotopy, and eventually arrive at the idea that the fixed point set components can be connected in a linear chain, one after the other. And you can do them in any order you wish. So you can, for example, arrange the components of the fixed point set into increasing Betty number. Once you've done that, then you perhaps have some principal edges remaining. Since now the main core of the space is connected, one can change the attaching maps for these remaining edges until they are all being attached at a single vertex. Any one will do. I choose the one to the far right in the picture as a way of formalizing it. So that's the process. Reduce out extra edges, then arrange to connect the fixed points in a nice way by principal edges, then add the extra edges in a more or less unique way. So here's a picture. We'll have a typical normalized diagram. The black stuff consists of fixed points. So if you had a reduced group action, this one has 4 components of the fixed point set. There's a wedge of 2 circles, another wedge of 2 circles, a circle, and an isolated point. The next step is to connect those components. So some principal edges connect them. I've drawn those in. I've chosen some in blue. Now, in general, if you made a random choice, that those 3 things might be connected like a tree, like a triad, or they might be in a different order. But there are some little lemmas you can argue that you can re-choose the picture to make it like this, which is to say the highest degree vertices to the left, then stepping down until you get down to the lowest degree on the right. And finally, you have some principal edges that have to be attached to this that we haven't accounted for yet. And those up to G homotopy can all be assumed to be attached at one point. I've put them there at the end. So my color coding now for these pictures of semi-free group actions is black for fixed points, blue for some principal edges that connect the fixed point set in a minimal sort of way, and then red for the principal edges that we have to add to fill out the rest of the diagram. This is the orbit diagram. Upstairs, of course, the blue edges would be covered by order of G blue edges, all with the same fixed endpoints being permuted. And here you would have these little bouquets of red circles upstairs that are being rotated among themselves freely. So from that picture, here are the sorts of things we can say. I've got several pages with statements like this. two semi-free G actions on a finite connected one complexes with fixed points are G homotopy equivalent in this weak sense up to a conjugation of the group, if and only if they have the actual identical normal form. To justify that completely, maybe one needs to look a little deeper at the homology. You can describe the representation on the homology just like we did with that Z mod 3 action back at the very beginning. If the finite group acts semi-freely on a finite connected one complex with non-empty fixed point set, then the representation on homology is of this simple form. Some number of Z's fixed by the group, some number of augmentation ideals, and some number of group rings. In the picture, the black circles, the fixed circles, give the T. So we actually have 5 fixed circles here. So the fixed representation is 5 copies of Z. We have the 3 connecting principal edges that give rise to group rings. So this one has I of G to the 3. And then we have those red circles, each of which is covered order of G times. So we have 2 copies of the group ring. Well, this is sort of interesting. I knew a priori that the representation looked like that among all integral representations when I was thinking about cyclic groups of order P. The same decomposition of the representations comes up various ways. The representations of Z mod P are completely classified, the integral representations, and they look like these together with some that correspond to exotic ideal classes in the group ring. And for abstract reasons, those exotic classes can't appear. But here, we just get it directly by a direct geometric argument without any question. So what we see here down, let me just emphasize down at the bottom. If you have a representation like this, A plus 1 is the number of components of the fixed point set, and the T is the Betti number, the total Betti number of the fixed point set. Another observation you can make at this point is that if you have any representation of this form, then you can realize it by a semi-free group action. The idea is just take T circles. So let's say we want to have, if you have this representation, you have A plus 1 components of the fixed point set. So take those T circles and put them at one point and take some isolated points, and then throw on some group rings, and then you will build an orbit complex with the labeling that you want for that to happen. And then it's essentially trivial to find the covering that would correspond to that labeled one complex. You can also use this perspective to count the possibilities for how many different ways you can do this. Suppose you have a representation of the form Z to the T, I of G to the A, and Z of G to the R. How many ways can you realize it? Well, I just said you could realize it. We know that you have to have A plus 1 components of the fixed point set. What we don't have in the representation on homology is how the fixed point set is broken up into different circles. How the first Betti number is distributed among the different components. So in fact, you can, as long as you have the right total P, you can assemble those circles wherever you want among those different components. So one way of saying this is that for every partition of T into at most A plus 1 parts, you can create a group action that has that form. you could do a similar thing with, if you wanted to look at groups of automorphisms as opposed to groups of outer automorphisms by keeping track of a fixed point. Then you have the question of where is your base point going to be among the different components of the fixed point. So again, you have an effective way of counting the possibilities. I had one issue here. In my hypothesis, I had the hypothesis that I had a non-empty fixed point set. So that means we really need to think a little bit about the case of semi-free actions that don't have any fixed points, namely the free actions. So what does the representation look like, and how does it fit in with what I've just been talking about? I have just a few words to say about that. Well, one conclusion is going to be that for cyclic group of prime order, things are pretty clear. For general finite groups, there are still some mysteries here to be pondered. So it's a theorem that goes back at least to Gauchet's in the 1950s, that if a finite group G acts on a finite connected one complex, then the representation on rational homology is as simple as you can imagine: a Q plus a rational group ring, or a number of them, however many you might need. It's an interesting point here. This sort of says the rational homology isn't very interesting. It doesn't matter what the group is, right? But the integral homology is kind of interesting. But even the rational, still, it turns out, some recent work by Favre and Hensel show that there's some interesting, potentially interesting submodules of the rational first homology. And they think about free actions of finite groups, or in other words, covering spaces, and identify something called the primitive homology. That's the homology that comes from lifting primitive classes in the target orbit space, and is related to a similar concept that's been useful in studying surface topology. So what would we say about the integral homology of a space with a free action of a finite group? One-dimensional, finite connected one-dimensional complex. The way you get your hands on this is to realize that you're actually talking about regular covering, finite regular coverings. And finite regular coverings are classified by homomorphisms from the fundamental group of the base onto the group in question, the fundamental group of the base. Well, we're talking about one complexes, so that's a free group. So we're talking about a homomorphism from a free group onto a group. Since the group is free, that's the same thing as specifying a sequence of elements of the group that generate it. And you can see the homology that we're talking about in this case is being given by the relation module abelianized, the kernel of that representation. So one can try to get your hands on this representation by trying to understand this representation rho a little bit. Most of the literature actually works the other way around. You're trying to understand these representations, ways of generating a finite group. How many inequivalent ways are there? You might use representation theory to distinguish ways, as opposed to what I've tried to do. So the way to think about this is thinking about Nielsen equivalents. So you can change the representation by an automorphism of Fn, or by an automorphism of G, to talk about weak equivalents. And so you can do this rather algorithmically by taking a basis for Fn and doing these Nielsen moves on them. Any automorphism of the free group comes from these Nielsen moves. And if you have a little luck, any two generating n tuples for a group are weakly equivalent. But of course, people have looked at this pretty hard, and for sufficiently complicated groups, you can find inequivalent generating n tuples, which doesn't help me very much for my problem. Nonetheless, if you carry this through in the case of abelian groups, then to generate a finite abelian group, you need your free group to have rank at least as big as the rank of the group, the minimum number of generators of the group. In that case, there's an essentially unique surjective homomorphism. Again, I'm allowing for automorphisms of the group G as well as automorphisms of the group Fn. And that gives us some information about group action on the representation space. A corollary of this that applies in the case of a cyclic group is that, on the one hand, by the theorem, there's an essentially unique surjective homomorphism. In the case of a cyclic group, we know what that unique homomorphism should be. It takes the first generator of the free group to a generator of the cyclic group and sends all the other generators of the free group trivially. And in that way, we see that the homology in question is pretty easy to read off. Here's the Z that corresponds to the element that's going to the generator, and here's the set of group rings that come from the elements in the free group that are mapped trivially. Corresponds exactly to the picture way back at the beginning of my talk. I haven't proved it, but almost surely that integral formula can never hold for a non-cyclic group. So let's wind things up here by thinking through, for the case of a finite cyclic group of prime order, where the action is always semi-free. In this case, we achieve what was my goal at the beginning, to see how to enumerate all the possibilities in an effective way. So we fix an integer n and a prime p, and we calculate the number of ways that the cyclic group of order p can act on a one complex xn of the homotopy type of a wedge of n circles. So what you have to do is you have to start off with, my idea is to start off with a representation. That's your first invariant. So you can systematically look at all the different ways you can write your n as a integral combination of p and p minus 1 for the group ring and 1. So that's a fairly trivial little program to write, to just spit out numbers like that. What we know is that for each such triple T, A, and R, the number of ways of realizing that representation by a group action with fixed point set is the number of partitions of T into at most A plus 1 points, how to spread the circles of fixed points out among the components of the fixed point set. That's what we had done before. Now we can say to ourselves, well, what if there weren't any fixed point sets at all? Well, that could occur in the case when the representation has the form Z plus copies of the group ring. That's T equals 1 and A equals 0 in our terminology up above. So if the n is congruent to 1 mod P, then you get one more group action, a free action of that finite group on the one complex. So we get an effective and explicit, easy calculation of all the possible inequivalent group actions in that case. Let me close with a couple of questions. What are the loose ends here? The question I have is, what if the representation looks like our standard representation that I'm talking about? But I don't know that the action is necessarily semi-free. Can this happen? Well, it certainly can happen. Can it happen if you're allowed to normalize up to G homotopy? Well, I'm not so sure. So my little dream would be that if you have an arbitrary finite group, not just a cyclic group of order P, acting and not necessarily semi-freely, but its representation looks like it should be coming from a semi-free action, then it would. I'm not making this as a conjecture, it's a question. A slightly weaker conjecture or question would be, if you have a finite group acting on a complex with this standard representation that looks like it should be semi-free with some fixed points, does it at least have a global fixed point? Well, there's this is where you can refer to the Lefschetz number that I mentioned way back at the beginning of the talk. And what you realize in this situation is that all the elements of the group have fixed point sets. But the question is there a global fixed point for the group action? So this is still some work, or shall I say play, thinking about these questions. It works in a couple of cases that we've already talked about, if the representation is trivial, or if we have a cyclic group of prime order, of course. And one other case where I've been able to work this out is in the case of a solvable group and a representation that looks like a group ring, which is the case where you expect to have a single fixed point up to G homotopy. And in fact, that's what works out. A good stopping point here, I think. Before I take a few questions, let me add just a last word. Congratulations, Rami. It's a milestone. I hope to be there one day, not so long from now. And best wishes for the years to come. Thank you, everybody.
Thank you, Professor Edmonds. And let's thank the speaker. And I'll ask everyone if there are questions.
And if you complicate the group, like group being a finite simple group, not K not P,
right?
Then I think there should be, I think, almost like a rational group ring.
You're muted now, so.
Yeah, you know, the finite groups acting on surfaces.
Right.
That is the lot of structure on the action on the first homology,
right,
with Z coefficients, Q coefficients, R coefficients, C coefficients. It is a complex structure and all that. And so there, the actions of finite simple groups, non-abelian, they are rather rigid.
Right, right.
If the genus is small.
Right.
Yeah, so I don't know exactly what question to ask. So would that be of interest from the just the homology or homotopy point of view?
I'm not sure. I know that.
No, I'm not asking you a precise question.
Yeah, one of the other speakers in this conference, because of the time zone, Alexander Mednik has done some work on finite groups acting on one complexes, where he's
Yeah.
tried to connect closer to the situation on surfaces. So he talks about something called, he calls them harmonic group actions. So he doesn't allow any, he looks at finite group actions on one complexes where there are no fixed edges. The fixed points are all just vertices, and tries to make some connections with some of the things that we've done on surfaces before that you're talking about. So there's some potential there for that kind of a group action, but that's still, I don't know how close the connection can be made. One moral of what I did, of course, with I was really thinking about Z mod P actions, but I realized as long as I said semi-free, the structure was the same all the way through. So one has to start allowing for all these different isotropic groups somehow or other.
So are there any advances after that Brodon's book on compact transformations group? And in special thing to apply to finite groups? Are there any major advances?
In general, well, there's a lot of algebraic topology that's
yes,
been done. Yeah, so
I see.
pushing the Borel spectral sequence as far as it can go, for example.
Yeah, right.
Any other questions?
Yeah, thank you. Thank you for giving me the opportunity to listen to you again with your homological, homotopical insights. Thank you.
It's been fun.
Yeah, I have one question. So yeah, Christian, you can go ahead.
আমি হাততালি দিলাম, তুমি কোশ্চেন করো।
Oh, okay. Sorry. So I just wanted to ask that the group action, when you are looking at, is there any consequence of the extensions of those groups? For instance, if you look at the Schur covers of this group, I mean, I looked at the notations you were using closely, and then this kind of looks like there could be something about it.
Right. Potentially, in this discussion of free actions of finite groups.
Yeah.
That question of the Schur multipliers certainly comes up.
Yeah, so maybe you can classify the multipliers over there. Semi-free actions.
The particular issue that I was aware of was with trying to classify free actions of finite groups on surfaces, perhaps up to cobordism, perhaps up to cobordism that allows fixed points. So an interesting question that's been worked on. So if you don't allow fixed points, if you're only talking about free actions, then it's a question of just equivariant cobordism theory. But if you allow fixed points in the interior, so here's some people working on these problems have found ways of showing that there are finite group actions for sufficiently interesting finite groups. There are free actions of certain finite groups on surfaces that do not bound an action on a three manifold, no matter how general the action on a three manifold might be.
Yeah.
So that involves some
equality of the Schur multiplier is kind of classified.
Yes, exactly. Whether the Schur multiplier is generated by by torus classes, for example.
Yeah, exactly.
That's part of what happens there. Yeah.
Okay, is there any questions?
I'll be off for lunch. I suppose you're heading for dinner by now.
Okay, yeah, sure. Okay, if there are no questions, thank the speaker again.
Yeah. So I thank the chairperson, Siddharth Sarkar, who chaired these last 3 talks. And now this differential geometry section of this Kulkarni at AT conference is over. I thank all the speakers, very distinguished mathematicians who have talked in this conference in the differential geometry section, and also all the chairpersons for all these talks. Now, tomorrow is the last day, and tomorrow there will be lectures on different other topics in mathematics. It is also likely that because some of the speakers, participants have suggested that there should be a proceedings of this thing, in that case, we would like to request all the speakers to write on their talks. We appeal to them to write on their talks. That will be very good for the proceedings. So with this, I thank all of you again. And now we close today's session. And tomorrow we shall meet at 9:30 IST. Thank you very much.
How is check